Hello, my name is Gavin Brown, and I'm going to talk to you today about memorization of training data in machine learning. This is joint work with Mark Bunn and Adam Smith, who are also at Boston University, and with Vitaly Feldman and Kunal Talwar, who are at Apple. Machine learning models contain information about their training data. This is kind of the point. Our result is that in natural settings, memorization of almost entire examples is necessary, no matter the learning algorithm you use, and even when many of the details that are memorized are irrelevant to the task at hand. Memorization is sometimes an explicit part of the training process. For instance, the famous k-nearest neighbors classifier contains a description of the entire data set. This is not a surprise. This is really what it's designed to do. But memorization can sometimes happen in unexpected places. Recent work by Nicholas Carlini and a large group of authors shows that OpenAI's GPT-2 text model memorizes huge amounts of irrelevant data. Specifically, and most strikingly, they've shown that it's memorized individual people's details, such as phone numbers and email addresses. This is very concerning, but also fascinating. I also want to point out that it's different than what has been sometimes called a phenomenon that is sometimes called memorization in the literature, referring to the memorization of training labels. Most relevantly, recent work by my collaborator Vitaly Feldman at STOC 2020 showed that there are settings where any successful algorithm must memorize the training labels. Our work can be seen as a strengthening of this, showing that any successful algorithm must memorize entire features of the training data, not just the labels. To state our main result, let me walk through our setup. We'll have a data set X, which will be n rows, n samples drawn IID from some distribution P. The data will be binary and it will be d-dimensional. Our results are most interesting when D is at least as large as N in this kind of high dimensional setting. We'll be doing classification, so we'll have labels that will maybe like binary or multi-class. And then in the standard way, we'll feed this data set to a learning algorithm that will output some classifier M, which we'll also call the model. The classifier will be tested according to misclassification error. So we'll sample a test point Y from the same distribution, and then judge if M is correct or incorrect on that test point. We'll call the error of the classifier the probability of an incorrect prediction over this whole process, the probability of drawing the data set and the test point and any coins of the algorithm. The central motivating question is, what does the classifier M tell us about the data X? Our main result, informally, is that there are natural tasks such that for every learning algorithm with error close to optimal, a small constant, 0.1 isn't important, such that the mutual information between the data and the classifier is big omega of n times d. So recall that the bit length of the data is an upper bound on the mutual information. So this lower bound is asymptotically the best thing that we could hope to prove. To really state the result, I'll need to talk about what the learning algorithm knows. And so the change we're going to make to that previous setup is that before we draw the data, we're going to sample the problem instance, the distribution over labeled examples, from some meta distribution or prior Q. So the distribution over labeled examples will itself be a random variable. After drawing that, we'll draw the data. The learning algorithm will know Q. It will know what kind of game it's playing, but P will be a priori unknown. This is crucial to our results because if the learning algorithm knew the distribution itself, it could just write down a model that ignored the data entirely. We'll then call the error of the classifier the error over this whole process, the probability of incorrect classification over this whole process. First, sampling the problem instance, then the data set and the test sample and any coins of the algorithm. I should point out that now that we've introduced this prior, there is a well-defined Bayes optimal classifier that minimizes this misclassification error. This Bayes optimal classifier necessarily exposes a lot of information about the training data, and we show that anything close to it also must. So our theorem, our main result, is that for any sample size n and dimension d, there is a natural task q such that for every learning algorithm with error close to optimal, the mutual information between the data and the classifier conditioned on the problem instance is big omega of n times d. So this opt-in d is the Bayes optimal error for this task. The fact that we're conditioning on the problem instance, conditioning on p, means that we're talking about irrelevant information, what is really unique to the data and doesn't tell you anything about the problem instance. In our setup, this will show up as noise in the data set or useless features that aren't used in the classification. So we show that any learning algorithm must memorize a lot of data, and furthermore, a lot of what it memorizes must be, in fact, irrelevant to the task. Again, this is our main central result. Let me give you an example of a learning task that we consider and can show memorization for. It's called hypercube clusters, and the data will be drawn from a mixture of clusters on the hypercube. So each cluster will be defined by a sparse set of fixed bits. To generate data from that cluster, what we'll do is we'll take our d bit string, we'll fix those specific bits to their specific values, and we'll fill everything else in randomly. What this results in is that points from the same cluster will appear slightly closer together in Hamming distance than you would expect from random chance. The learning task then is given a fresh data point, can I tell what cluster it came from? And what's going on here informally is that if I give you a bunch of examples, not too many, but many, examples from a specific cluster, a single cluster, you'll be able to learn what the fixed bits are exactly, almost exactly. But if I give you only a few examples from one cluster, or in particular, if I give you exactly one example from a cluster, you will not be able to discern which bits are fixed and which bits are totally irrelevant. And so a successful algorithm will have to keep them all around if it hopes to succeed at test time. We'll get back to this more formally later. There's a lot of related work on memorization and machine learning, and I want to point out a few areas that are most relevant to what we're doing. So as I mentioned, work by my collaborator Vitaly Feldman shows settings where any model must memorize the labels. Ours is a strengthening of this to talking about memorizing the features of the data set as well. Additionally, there's a line of work on what are called learners that leave little information, studying the same exact problem. How much does the classifier tell me about the data set? Most relevant to our results is a recent paper by Roy Livni and Shai Moran, which provides lower bounds for the PAC-Bayes framework, showing limitations of that style of analysis. As a result of the theorems they prove, you can provide a lower bound for some learning problems of the form omega n log d. So recall that our lower bound is n log d. And so our work is a strengthening of that result of theirs, although of course theirs also has a different purpose with this PAC-Bayes analysis. It's possible that their argument could be strengthened to a lower bound of n log d, but that seems the best that particular analysis could hope for. Additionally, there's a line of work on representation complexity, which is used in studying the sample complexity of differentially private learning. Representation complexity provides lower bounds on model size for a specific concept class C. In our setup, we don't have a concept class. We have this distribution over prior distribution over labeled examples. But representation complexity, kind of morally, is talking about how much information about P must I encode to succeed at this task. And so you can think of it as providing a lower bound on the mutual information between the problem instance and the model. How much does the model have to describe about the task to succeed? While our lower bound, the mutual information between the data and the model conditioned on the problem instance, is like what is unique to the data set. So there's this kind of subtle distinction between these points, but important. Additionally, there's a line of work on time-space trade-offs for learning by many authors, but notably, including but not limited to Ron Raz and his collaborators, that provide lower bounds for streaming style learning, where the data points arrive one at a time. The foremost example is d-bit parity learning, which is shown to require either d squared memory, which is the lower bound that's matched by the upper bound from Gaussian elimination, or if you use less memory than that, exponentially many samples, just kind of guess and check. Our results are on the size of the final model, which provides a lower bound on the size needed during computation. Stated slightly differently, our results say to compete with the best learner on a specific number of endpoints, you need a large model. We believe that our results could be turned into some type of time-space trade-offs with a similar flavor, but probably not such a sharp exponential jump in sample complexity. Additionally, our results may be interesting from the lens of information bottlenecks or minimum description length, which are two tools that have something to weigh in on what we're doing. I want to suggest that the giant state-of-the-art models that dominate machine learning today might actually be unavoidable. GPT-3, the successor to the GPT-2 text model we saw before, takes 700 gigabytes uncompressed. And furthermore, I want to put forward the idea that this might not just be because the tasks themselves are big. Of course, we don't expect there to be a succinct model of the English language. Any generative language model must be very big. But maybe models have to be even bigger because they have to keep around lots of information that turns out to be useless. Of course, we've seen this experimentally, and our works point towards this theoretically as well. Additionally, our work shows new ways in which privacy is hard. Differential privacy is a formal framework for limiting the privacy leakage from statistical analysis. It's not stated in terms of mutual information, but there are clean upper bounds for differentially private algorithms on the mutual information that can be leaked. In particular, these upper bounds for reasonably private algorithms contrast with our lower bounds, and so no really private algorithm can succeed at our tasks. This in and of itself is nothing new. There are a number of very striking separations from what can be done privately versus non-privately. But our work highlights a new way that privacy can't be achieved, in that it might be the subpopulations that we most want to protect, the underrepresented subpopulations that are at highest risk for exposure, because those are the data points from which the model wants to extract the most information to achieve high accuracy overall. So far we've stated the main result and had a little bit of a discussion. I want to formally state what the learning tasks look like. And then finally, I'll talk a little bit about how the proofs are set up by talking about the information complexity of certain communication games related to our learning tasks. The learning tasks we consider will all, like the hypercube cluster example, be a mixture of many clusters. And a distribution over labeled examples will be specified first by a set of mixture coefficients. For this talk, it's fine to think of just a uniform mixture over clusters, although you can get different flavors of results with different sets of mixtures coefficients. Then for each cluster, for each subpopulation, we'll need a specific distribution for that subpopulation, denoted P sub j. This P sub j will determine the rules or the label for that subpopulation. And each of these will be generated independently from some prior distribution. So let's take a look at what these per subpopulation distributions actually look like. The first, the hypercube clusters, like we said, the P sub j is described by a sparse set of fixed bits or fixed features I sub j, each of which is chosen to be fixed independently with probability rho. once we've chosen that that bit will be fixed, we choose uniformly a value. It's either going to be 0 or 1. And then to generate samples from that distribution, we first fix those specific bits and fill everything else in randomly, uniformly at random. And the label is J, just the subpopulation. So this is meant to abstract any kind of high-dimensional multi-class problem, such as image labeling. The next task is meant to abstract sequence prediction or language modeling, like what we saw before in the Carlini et al. Paper. This next symbol prediction task, each P sub j is associated with a uniformly chosen reference string. And then to generate an example from P sub j, we take a prefix of random length, we add some noise uniformly at random, and then the label is the next bit, which could also possibly be noisy. This next symbol prediction task is kind of a cousin to the augmented indexing problem from communication complexity. And the hypercube clusters task is kind of like the famous gap Hamming problem from communication complexity, which is exactly this problem of determining if inputs are close or far apart. And both of these problems our proofs rely on ideas that have appeared in the literature for these problems. Our lower bounds are established by looking at singletons in the data set. This idea comes from the previous work of my collaborator, Vitaly Feltman. The idea is, after we draw samples from this mixture over subpopulations, some of our subpopulations will receive many data points, some will receive none, and some will receive exactly one data point, one representative in the data. And we call these subpopulations, we call these data points the singletons, and we focus our proof on them. We show that a typical data set in our setting has a constant fraction of the data points being singletons. And we establish a series of reductions, showing first that if you're accurate overall on the learning problem, you must be accurate when the test sample comes from a singleton subpopulation. This proof is just a couple lines of algebra. There are many singletons. They represent a lot of the probability mass. The second step, which is harder, says that if you're accurate on the singletons, then you must reveal near complete information about those singletons. To establish this step, we prove new information complexity lower bounds. So to finish up, let me talk a little bit about what these lower bounds look like in the case of the hypercube cluster task. We proposed a communication game that we call the singletons only game, where there will be k subpopulations drawn independently and uniformly at random, or independently from the prior. And Alice is going to get one singleton from each subpopulation. So she'll get k times d bits overall. And Bob is going to get a singleton, get a data point drawn from one of those subpopulations, and it'll be his job to guess which one it is, just like in the hypercube task. So the first step we do is in the original game, each of these bits were chosen to be fixed with some small probability row, resulting in some number of fixed bits and some number of uniformly random ones. The first step of our proof is to show that this task, this singletons only game, is equivalent to a nearest neighbor game, where Alice's data points are uniformly random and independent, and Bob gets a corrupted version of one of Alice's data points. Bob's sample will appear slightly closer than you would expect to one of Alice's data points. And in particular, we can show that this is equivalent to generating Bob's sample by running Alice's sample through a binary symmetric channel with parameter 1 minus rho over 2, something that's almost half, almost all the bits get reflipped. So we show that solving this singletons only hypercube cluster game is equivalent to solving this simpler to analyze nearest neighbor game. Then for the nearest neighbor game, we're able to prove a new lower bound that shows that says if Bob succeeds with a small constant probability close to optimal, then the mutual information between the data and the model must be big omega of k times d, asymptotically the best one could hope for. This proof relies on a strong data processing inequality for binary symmetric channels, and its use is analogous to its use in a recent paper lower bounding the information complexity for the gap hamming problem, which I said is kind of like a two-sample analog of our K-sample problem. We conjecture that our lower bound can be improved to 1 minus little o of 1, which would be the correct constant, which would mean that Alice has to reveal almost all the information about her singletons as the error goes to 0, a qualitatively stronger statement. In conclusion, we showed that there are natural tasks where naturalness is not formally defined here, such that for every learning algorithm with error close to optimal, the mutual information between the data and the classifier conditioned on the problem instance is big omega of n times d. And we talked about how this conditioning on the problem instance captures what is unique to the data, the fact that we're forced to memorize a lot of irrelevant information. In the paper, we provide some simple experiments showing efficient attacks on models that are able to recover these singleton examples. We provide lower bounds for other problems, including the next symbol prediction task we showed, and threshold learning. For these problems, we are able to prove stronger statements that one must memorize the entirety of the singletons as the error goes to 0, like what we conjectured could be done for the hypercube clusters task. And finally, I want to leave you with reason for optimism. In our tasks, the hard distribution is tailored to the sample size. But if you fix the task and let the sample size grow to infinity, the need for memorization decreases. And eventually, you're able to learn something that is almost independent of the data set. And so this memorization behavior disappears as in this parameter regime. So I want to thank you very much for listening to my talk. I hope to see you at the conference and talk to you then.